I'm Jason Hupp. I'm an application scientist here, and I'm going to walk you through the components and some sort of basic operation of the LI-6800 and show you a whole bunch of cool features and things that it does that really no other instrument does. So I have two sensor heads sitting here, and they have two different chambers on them. One of them is our 3x3 chamber with a light source. This is a red and blue light source. And the other one is our multi-phase flash fluorometer. And then this is the instrument console. So the way these guys are kind of divided up, you know, this sensor head right now is connected to this console. And what I like to tell people is it looks like one instrument, and users will interact with it as one instrument. But the 6800 is a large leap forward in technology based on the way that Li-Cor has done instruments in the past. And what looks like one instrument to a user and feels like one instrument is actually three separate instruments that are sitting here, right? The fluorometer is a device unto itself, the sensor head is a device unto itself, and the console is a device unto itself. And they complement each other, and the way they interact with each other is pretty cool. So these things are all Ethernet-based devices. They use standard TCP/IP protocols. They talk to each other and your computer the same way that your computer talks to the internet and every other computer out there in the world. If you've used a 6400 before, you remember big, heavy clamshell connectors, D-connectors with clamshell cases on them and big, thick cables. And you'll notice that we've gone to a much skinnier cable here with a LIMO-style connector on it. And these cables are power and Ethernet. And one of these exists for the fluorometer, and one of them exists for the sensor head. The fact that everything is Ethernet lets us do some kind of cool stuff with the instrument. You'll note that the way the ports are labeled on the side of the console is we have one port that's called head 1, and we have one port that's called head 2, right? And because they're Ethernet with power, they're all pretty much the same. You plug something in, it figures out what's there, and it makes it such that if a connector will fit and you plug it in there, it'll work, okay? So another thing to note is that we only have a single tube coming out of the console going up to the sensor head. Unlike other gas exchange systems, the whole meat of the gas exchange system is in this sensor head, right? So this tube brings a single cohort of air from the console to the sensor head. And then inside the sensor head, there's a match valve, there's some electronics that drive things, the ergas set about here, mixing fan and temperature controller inside here, and then like I said earlier, this is the chamber. Once this tube enters, there's a short section of plastic tubing, and then everything is metal and O-ring sealed from that point forward. That means that the flow split and the flow control are all embedded inside the sensor head. And in a moment, when I start going through environmental controls on the instrument, I'll show you what that flow path looks like and some of the cool things that we do with it. For sort of general features of the sensor head, so we have a handle. It's more ergonomically designed than our predecessor, right? It's set at a reasonable balance point for the sensor head so that it doesn't provide a lot of strain on the wrist. Tension on the chamber closure set by springs, right? That means there's no adjustment for chamber tension that the user needs to make. The chamber bottom more or less floats in a few different axes, right? I can twist this thing around, and this allows for an even clamping pressure, right? The chamber bottom approaches the chamber top parallel to each other, right? And I can accommodate thin things like a leaf in here, or I can clamp on something relatively thick like my hand. I still get even pressure. I still make a relatively good seal, maybe not on my fingers, and then I can still clamp it back on something thin. We give you three positions for the chamber handle. There's all the way open, there's a park position that reduces strain on the gaskets, and then there's closed for measurements, right? Some other features of the sensor head. So we have a keypad here This has a log button and then 2 right and left arrow keys that allow us to access this little heads-up display on the sensor head. And if I push these keys, you'll see that the data here scrolls and I can look at various screens. We have a quantum sensor on the sensor head, much like we had on the 6400. So I said this was a fluorometer. This is our 3x3 chamber. The 3x3 chamber has 2 sort of operational configurations, right? We can use it with a light source, or we can use it as a clear top chamber. The light source comes off with 2 screws, and then there's a propofilm seal at the top of the chamber. The nice thing about this is, whether you're using it with a light source or not, if you have leaves that are irregular, right, you have a clear view into a sealed chamber and a light source that comes off quickly with 2 screws. That means that I can take something like a camera and I can image the leaf while it's still clamped inside the chamber to compute leaf area after the fact. Let me put this guy back on here. So the way the chambers come on and off the instrument, they're modular. So the chamber comes off as an entire assembly. There's no individual little pieces. There's no little O-rings that can fall out. There's a few connections on the bottom side of the sensor head. These are normally covered with a skid plate. You can see it on this chamber. These connections, we have a connection for the PAR sensor. These use stereo jacks. We have a connection for a leaf temperature thermocouple, also with a stereo jack. You'll note that they're labeled here, and then we have one called T1 and one called T2. The instrument supports, and I'll show you this in software, the capability to plug in multiple leaf temperature sensors at the same time. And then we have this port called LS, which is a light source connection. So if we disconnect those guys and we pull this little cable out, I'll show you the back side of the chamber. So we have to remove 4 screws to take a chamber off. So the 2 that hold the springs onto the latch mechanism. And then there are 2 captive screws in the base of the chamber. And when the chamber comes off, you have access. You can see the mixing fan, you can see a couple of filters. I'll show you where these are in the flow path when we talk about it on the instrument. But the real motivation for me taking this off is to show you no O-rings and to show you this little connector right here. So there's a little computer chip associated with this. This holds identifying information about the chamber. It holds calibration information associated with the accessory. And when I plug this into an instrument and turn the instrument on, the instrument knows what chamber is there, and it changes its configuration automatically without the user having to do anything, right? If you've worked with the 6400 before, and we talk about configurations with that instrument, you'll often hear us call it a dumb instrument, right? Because it doesn't know what's attached to it. It relies on the user to tell it. So using that same analogy, our 6800 is a smart instrument because it knows what's plugged into it, and it knows inherently what it needs to do and change its software to use that device. So let's talk about software. When you turn the instrument on, you get a screen that looks like this. Right now you can see that it's detected that it has a fluorometer chamber attached to it, and by default it's going to do complete gas exchange computations and use it as a full fluorometer. We can get some settings from the instrument. The way the console interface is laid out, right? So we have a ribbon across the top that has sort of our main components of the software. And then under any one of these main components, we have another column and maybe a ribbon across the bottom that gives us sub-features of that software. I guess I didn't talk about this with hardware. Now is as good a time as any. You'll note that there's a little countdown up here at the top. So this instrument uses a modern battery technology, and it's a high charge density, so we get a lot of runtime. And we also tell you how much runtime is left on those batteries. Right now, my instrument's operating on its own, independently running from battery power, so this is how much charge is left in my batteries, 7.5 hours. On the side of my instrument, I have a connection that lets me plug it into the wall. And if I were plugged into the wall right now, this would change to tell me how long it'll be until the batteries are fully charged. And just like its predecessor, the 6400, batteries are hot swappable on the 6800. So this is the battery that we're using. It has a built-in charge indicator telling me that this battery is fully charged. Because the instrument's a smart instrument, there's not a whole lot that you have to do with user configurations. There's settings you can change on the instrument. I'll show you some of those. But for the most part, besides starting here, you're not going to do a lot on this screen. We have a lot of computing capacity and a lot of integrated sensors built into the device, much more than what's necessary to do the actual measurement that we need to do. And this lets us do some pretty cool things. So if you were a 6400 user and you took a 6400 and you were getting it ready to go into the field, you would open up book 1 of the user manual and you'd go to page 1 of chapter 4, and there'd be this checklist of things that you would go through. And that checklist would require you to push buttons and turn knobs and shake things and touch thermocouples and get screwdrivers out and turn things. And after 20 or 30 minutes of your time working with the instrument, you would know that the instrument's working well and you can take it out and go make measurements with it. So with a 6800, I don't have a screwdriver, there's not very many knobs. I just hit this green start button and I go away, and in about 10 minutes I come back and it gives me a summary of what passed and failed, right? And what I did here was I ran this test just a few minutes ago because we don't want to sit and watch it go through it for 10 minutes. And I had one failed test. It says, is P chamber within 0.005 of 0? And it measured it at minus 0.019. All right, that's a fairly small offset. I'm not particularly worried about it in the context of what we're doing today, but if I were going to actually make measurements with this instrument, well, I would go to this calibration screen and I would pull up the console that lets me adjust the P chamber calibration, and I would zero the pressure sensor. And that would be my full checkout before I took it in the field. All right. That's what I want to say about the startup panel. Let's look at some environmental controls because there's some neat stuff here. Let's start in flow. So flow gives me a diagram of the system flow path, right? And so I have a pump, and then I have a flow split with a flow meter associated with it. That flow split, let me back up. That pump is inside this console, all right? This little short straight line that's dark blue here is this tube going up to the sensor head. And then this flow split sets about right here in the sensor head. And then I have two flow paths that come out. I have one that goes to my sample chamber. That's this part. Comes from the sample chamber through a user controllable valve to apply an overpressure inside the chamber. It comes from that valve to our match valve and then on to the sample and reference analyzers, right? So reference path goes straight from the flow split through the match valve to the reference analyzer. I said something about having extra sensors, more than what we need for calculations. One of them is this, right? So I have this sensor measuring flow going into the sample chamber. That's what we use to compute assimilation and transpiration, right? But I also have flow sensors on the outflow from the two gas analyzers. And because I know flow going into the chamber and flow coming out of the chamber, I can compute an approximate leak rate, right? The flow meter going into the chamber, that's a high resolution flow meter. We need the high resolution to get a good measurement of assimilation, transpiration. The flow sensors coming out of the ergas, these are lower resolution. If they're within 40 or 50 micromoles of what's going in, I'm pretty happy, and that's about all we can expect out of them, right? But if this read 300 here instead of 740, then I would know that there was a significant leak causing me to lose air between the sample chamber and the erga, right? And we can demonstrate that simply by opening the chamber, and we should see that this number falls, our cartoon updates, and then we get a flow S low warning at the top of the screen, right? Before I show you water vapor and CO2 control, right? Because you'll note that water vapor has its own little icon here, right? It's not embedded within flow like it was on the 6400. Let's talk about sort of the components of the console that give us the control, right? So we have chemical columns on the back of the instrument. We have one that has soda lime, right? This strips air of carbon dioxide. We have one that has Dryrite. This is a desiccant. It pulls water vapor out of air. And then we have one that's full of Paul Stuttgarter mass, which is basically just a baked ceramic media. And then we have a source assembly for carbon dioxide, and this takes an 8-gram CO2 cartridge. So some neat things that I want to point out here. If you were a 6400 user, your instrument would have the equivalent of these two chemical columns. And your instrument has a knob at the top of both of them, right? And that knob allows the user of a 6400 to manually set the flow through those chemical columns, right? You can set what proportion of air you want to dry out. You can set whether you want to scrub CO2 or not scrub CO2. On our 6800 here, there are no knobs, right? Flow to these chemical columns is all set with valves inside the console that are under computer control. And that means to do things like water vapor control in our chamber, the instrument can automatically, for us, proportion the airstream between adding water to it and taking water out of it, which is pretty cool. And then a comment on the CO2. So we now use 8-gram CO2 cartridges. These are all food grade cartridges. Food grade means they don't put oil in them. And no oil in them means that there's no filter that a user has to mess with, right? So let's look at water vapor control. Much like our flow control screen, right? We have a diagram that updates in real time to show us what's happening. It's showing us now the flow through that humidifier column and through the desiccant column. Right now I'm set to control reference H2O at 20 millimoles per mole. For most measurements sort of done at the leaf level, we'd expect you to control on something like VPD leaf and maybe set it between 1 and 1.5 kPa. I don't have a leaf in there, so it doesn't really make sense to try and control in a vapor pressure deficit against something that doesn't exist at the moment. You know, we can change these and the instrument will respond, right? If I want to drop the humidity down just a little bit, we'll set it to 18 millimoles per mole. And the instrument should fairly quickly respond to that change and drop the water vapor down. You can see these little bars moving on the scale to show us where the current concentration is. And we're at 18. CO2 control works much the same way, right? We have another diagram. This diagram updates in real time to show us what's happening. We have our soda lime column and we have our CO2 source, right, with our CO2 cylinder in it. We have counters at the bottom, right? If I fill my column up with fresh soda lime and I tap this little counter, what it's going to do is it's going to compute over the runtime of the column how much CO2 it's absorbing, right? And so you have a metric on the instrument to sort of quantitatively tell as you're approaching exhaustion of the soda lime. And then the same deal with the CO2 source, right? So if I put a canister in here and I tap this to reset it, it's going to give me a count of how long that canister has been in there and been in use. Right now I'm controlling on my reference CO2 concentration, right? So that's like the concentration going into the chamber. And I've set it to 10 ppm. And I did this deliberately because this is one of the really cool features of the 6800, right? I have full control of CO2 from essentially 0 ppm to 2000 ppm. And I can control at pretty much any concentration I want in between there. So if I want to control at 10 ppm, I can control at 10 ppm. If you were a 6400 user and you wanted to control at 10 ppm, well, you'd be pretty much out of luck, right? Because the way the injector was configured in the 6400, you got control at 0, and then you got control at something in the 30, 40, maybe 50 ppm range, depending on your instrument, and you couldn't do anything in between without heavy user modification to the console, and there were trade-offs for that modification. In the 6800, if I want to do high resolution measurements at the low end of an ACI curve, I have the control capacity to do this, right? And if I want to set it to something different, something reflective of ambient, right, I can type in that value, and fairly quickly the instrument should go there. A big difference between this instrument and the 6400 in the way that it controls CO2 is that the 6400 was very fast to go down in CO2 concentration, okay? But it was very slow to go up in CO2 concentration, and that was a consequence of where the mixer sat relative to the pump. On my 6800, it's just as fast to go up in concentration as it is to go down in concentration. I was doing some demonstration measurements the other day. I'm not going to do it here, but I was doing step changes from 10 to 2000 ppm and then back down. And it took the instrument about 40 seconds to stabilize going up and then to stabilize going back down, which is pretty impressive. And we've stabilized pretty quickly here at 400. So this is fan speed control. Historically, we've called this fan a great many things. We call it the chamber fan, we call it the mixing fan, we call it the leaf fan. Here, we call it the mixing fan, although I'm sure if you talk to Li-Cor people, we're going to use all three names for it, just because that's the way we've always done it. We give you a lot of control options. If you were a 6400 user and you use the fan, then you would have seen that there are like 5 set points for the fan, right? 0, 1, 2, 3, 4, 5. And these were arbitrary set points that responded to some arbitrary control voltage that went to that fan, right? Here we give you the option to control fan based on rotations per minute. We give you a wide range over which to control. And we have feedback from the fan, so we know not just voltage that we're sending to it, but we also know the actual rate at which the fan is moving. So this has some consequences for the way we do things like boundary layer conductance on the instrument. So in a 6400, we would take that arbitrary fan speed and leaf area, and we would go to something that's more or less a lookup table, and we would come up with what your boundary layer conductance is. On a 6800, we use fan speed, leaf area, chamber geometry, in some cases the orientation of the leaf inside the chamber, and we model boundary layer conductance on the fly. And that's why we have a control option here for boundary layer conductance, right? So if I know the leaf area in my chamber before I make measurements, I can hit this, and then instead of making all my measurements at a constant fan speed, I can make all my measurements at a constant boundary layer conductance. Okay? Temperature control, I said I'd come back to this, right? We have the option for T1 or T2, right? These are leaf temperature sensors. If I have one sensor and I plug it into T2 and nothing in T1, the instrument will automatically map T2 to leaf temperature. If I have two sensors plugged in here, I'll get an extra column in this little green section of the diagram that shows me the measurements from T2, and then it'll give me some options for what to do with those measurements. Whether to map them to leaf temperature or to use an average of the two values. Okay? For light, so light source lets us pick the source that's connected to the instrument. You'll note here that it says head light source, console light source. When I flip the chamber over, I showed you one light source connector. On the side of the console, we have another connector called accessory. And at some point in the future, it's quite likely you will be able to plug a light source in here, right? Software is set up for it, hardware is set up for it. We don't have a cable currently, right? So I can pick what light source I'm operating and where it's at. In this case, I have a fluorometer connected to my sensor head. If I go to fluor light source, then this gives me the option to configure the actinic part of the fluorometer, turning light on and off, the light that drives photochemistry during gas exchange measurements or during a light-adapted fluorescence measurement. So if I hit actinic on and I open my chamber, it should have a nice bright light. I can change my target values, and this lets me proportion red and blue light coming out of the light source. We can do this same proportioning, right? We have independent control of red and blue in both the fluorometer and the 3x3 LED light source now. So if I just clear this and set it to 0, then my light should become all blue. And if I put a 9 back in here, right, by default we would do 90% red, 10% blue. If I just put a 0 in for my blue, my light should become all red. Right. And then I can turn that light off. For configuring the fluorescence part of the measurement, right, we have another sub-menu that shows up down here. This lets us configure the measuring light, the modulated light that's used to generate the fluorescent signal that we detect. We have options for rectangular flashes. This is like a traditional fluorescence measurement. We have options to configure the multi-phase flash. The fluorometer on the 6800 is really a high-speed fluorometer. It has a lot of power, a lot of capacity to it. And one of the features that it has that previous fluorometers from Li-Cor hasn't had is we give you the option to do induction kinetics. This is what's commonly referred to as an OGIP curve. And then we have this field called auxiliary, which is nice. You know, it's diagrammatic like everything else on the instrument. And this gives us access to this 25-pin auxiliary input connector on the instrument. And we can use this connector to connect different devices to the instrument. And I don't mean that Li-Cor makes other devices that plug in here with a crazy D connector like we've used since the 70s. I mean that the D connector acts as a breakout for user devices to be plugged into the instrument. So if you want to add extra sensors, or you want to use this to control things, then you can set this up as digital inputs or digital outputs, analog inputs. There's power supplies on here, and you can interface your own user devices with that connector. Okay, that's it for environment. Let's talk about constants real quick. So we have some system constants. We have some gas exchange constants. Gas exchange constants is where you find leaf area, right? We give you two options for leaf area on our chambers, right? So S, actual area inside the chamber. And if I hit the box, I can type something in, right? If I have 3.2, and my little diagram changes. If I have linear leaves, right, something like a grass that's going to cross the chamber, then what I can do is I can type in a leaf width directly, right? 0.56. I have a really narrow leaf going across it. And it will compute the leaf area based on the leaf width going through the chamber, and in the case of the fluorometer, it accounts for the curvature of the chamber as it does that. Leaf temperature, this lets me tell it whether it's measured or energy balance. Leaf light, these are weighting factors for light absorption and transmission in the chamber. User constants, this is something that we would have called prompts in previous instruments. This is where I can create a user-defined variable, right? Something like plot number, species, replicate, and I can create these variables, and then when I log data, the instrument will give me the option to input answers to them, and it will associate that data with the appropriate measurements in the final file that the instrument generates. Okay? Fluorometer has constants for the fluorometer. Stability definitions, these are much like what we used on the 6400. They're statistical definitions of what stable data looks like. We use stability definitions a few different ways, right? It's not uncommon for people to set up stability criteria or stability definitions and then send a group of users out in the field to make measurements, and then let the users use those stability definitions to decide when to log data. But probably the most common use for them is related to these things called auto programs. And auto programs let me do things like CO2 response curves. And the instrument, if I tell it a minimum and a maximum wait time, and I give it a stability definition, the instrument will use that stability definition to decide when the data is stable and log data for you. You can think about it as not just defining a time period in which you want it to record the data, but providing it with a window of time, and then the instrument can decide in that window whether things have reached stability and whether or not you have good data and it's worth recording or not. So that's what stability definitions are. I'll come back to log files here in a second. So if we look at measurements, so right now I have a real-time plot, and then I have a grid view on the instrument. The grid view shows me a whole bunch of things. Right now I have just kind of garbage data. I have not matched my instrument, so I see some weird value for assimilation. It's also partially driven by the fact that I put a ridiculously small leaf area in here. Let's go back to 6. Right. And then, so grid shows me real-time data numerically. Graphs show me graphs. Just like previous instruments, right, we have various graphs that are defined by letters. We have various grids that are defined by numbers. If I want to edit either one of these, right, so if I want to edit the grid, I can change the number that are displayed there, and I can pick any one of these, and I can go and pick a different value for it. There are a ton of values that you can look at on real time on the instrument. Those values are all grouped into categories, right? So this are the gas exchange values, and if I hit the arrow, wait, there we go. We can see the individual groupings, right? So these would be auxiliary inputs and constants, gas exchange, fluorescence parameters. We don't need to change any of these. I'll leave it at 4x3. Let's go ahead and match the ergos, because this is a major change on the instrument too, right? If you think back to that flow path that I showed you, the sample chamber and the sample erga have a physical separation between them. That separation is very, very tiny, but it's enough in combination with our match valve to let us do some cool things. And related to matching, right? So we have one of these. Watch this little diagram. If I go automatic, you're going to see the from chamber air is cut off and the reference air goes in, which means I can do things like open my chamber in the middle of matching and it won't affect the match that's done on the instrument, right? This means that we can give the instrument a lot of options to decide when to match for us without us having to remember to do it. You know, I'm hesitant to use the term idiot proof too strongly here, right? But there are a number of features of the 6800 that make it such that if I wanted to set up an instrument, I could configure it, and then I could go hand it to somebody that doesn't have a ton of knowledge about how to operate the instrument, and I could make it such that they could probably go get reasonable data for me with it, right? Because I can use stability criteria to decide about logging. The environment's fully under control of the instrument, right? There's no knobs, there's nothing for somebody to fiddle with. Once the numbers are set, the instrument will stay there. I have information about leaks, I have warnings when things go awry, and then hopefully it makes it just a lot more user-friendly and easy to use. Okay, so that's real-time data. Let's go talk about log files real quick. So this is what I'm talking about letting the instrument decide when to match for you, right? That's our top option under logging, right? Right now it says never match. I can pick only if, and it's going to go through this list of criteria. And if any one of these is met, it's going to go ahead and match for you. Logging options. These are things that let me configure the log file and what happens with logging. If I want to open a log file, I can do that here. I can create subfolders on the instrument in the same place. I have a bunch of log files on the instrument. I'm not going to log any data in the demo. But what I do want to show you is the way you get data off the instrument, right? So I said it's all Ethernet before, standard TCP/IP protocols. If I plug an Ethernet cable in here into my computer or into a network, I can treat this instrument as a network drive, and I can just click and drag data off of it, or I can use some secure file transfer program like WinSCP or FileZilla to get data off. But I don't have to do that, right? I do this stuff every day. I'm very comfortable with that. Most users, not quite as comfortable with these sort of next level networking type things, right? It's beyond what you do when you go to a web page every day. You'll also note that there are USB drive or ports for a USB drive here, right? So I can plug in a USB mass storage device, a thumb drive, a bigger drive. And if I go to export logs on the instrument, you'll see that I have all my data listed here. If I had a drive plugged in, I would have everything that's on that drive shown. And I can pick files and I can copy them to the USB file or USB drive. And then I can do the same thing. If for some reason I wanted to move data off of a USB device back onto the instrument, I can import log data. And then maybe the other thing that's worth seeing in here is analyze logs. All right, and if I were to pick one of these files, I don't know much about these, but let's try this one. And I hit view, right? I get a window that shows up. I can see some data. Let's look at gas exchange. Gas exchange looks reasonable. And I can create plots of this data on the instrument, right? So this data said it was an ACI curve. So let's go gas exchange. Let's pick CI. Let's go gas exchange and pick assimilation. And look at that. I can plot stored data on the instrument. I get something that looks nice. That's pretty much all the features of software, hardware that we want to talk about. Thank you.